Okay, so for functions and their inverses, okay, we have like subcategories like even functions, odd functions, rational functions, quadratic functions, and now a category of functions we're going to be looking into will be what are referred to as one-to-one functions, and those could be in the mix where you have like some quadratic functions, rational functions, radical functions, where they could be one-to-one. And now just for identifying characteristics, okay, now for what we have again in the case of a function, once again, is going to be a mathematical relation where, once again, if you're looking at the xy coordinate system, for each x value, again, just for the x value, okay, you're looking at the input or independent part of it. There's going to be one and only one corresponding y value. Okay, and the y value again is going to be the output or dependent variable. And for what we have, once again, what is going to define a one-to-one function. A one-to-one function is going to be a function whose inverse is also a function. And what I mean by inverse, not like multiplicative inverse, like multiplicative inverse of x is 1 over x. I don't mean it in that particular sense. What I mean by inverse, you could regard that as reverse. Okay, like inverse, you can have like interchanging. Okay, like you have reverse. Okay, like the function might have an ordered pair, and all ordered pairs are the form xy, and then you would have the inverse, okay, to be again just switching the order, where the inverse will have in its x and y coordinates, okay, what were the y and x coordinates in the function itself. Okay, so what I mean by inverse, in other words, I'm just switching the ordered pairs. And now some characteristics of what we have with one-to-one functions. Okay, first of all, when we looked at graphing, okay, now we had a function to satisfy the vertical line test. we would have at most for the graph of a function, we would have the intersection by at most 1 point for all x values between a vertical line and the graph of the function. You have the intersection at most 1 point. Now for a one-to-one function, okay, it's going to satisfy the vertical line test. Okay, we already have, like, for each x value there's only one corresponding y value. But guess what? It's going to also satisfy what is referred to as a horizontal line test. So just kind of reversing the language. Not only do you have one y value for each x value, but you can say that for each y value there is only one corresponding x value. So a one-to-one function is going to satisfy both the vertical line test and the horizontal line test. And just looking at what we have as examples of one-to-one functions. Okay. Now, when we first looked at functions, okay, we started out with ordered pairs, and we can do likewise with one-to-one functions. And we'll say that we have as a case, right, say we have a one-to-one function, and say we have our function f of x, and we'll say we have to be made up of the ordered pairs, and we'll say that we have 1, 3, 2, 5, 3, 7, as well as 4, 9. Okay, and if you notice, you have the x values of 1, 2, 3, and 4, and none of the x values will repeat. Okay, so each x value is paired up with 1 and only one corresponding y value. And okay, so just again, just taking what we have in the case of the domain, we have for the case of the x values, so you got 1, 2, 3, and 4. And we've been looking at that quite a bit time and again, and not so frequently. Now, we have for the y values, okay, that will be the set of what we refer to as the range. Okay, so the range, we have the corresponding y values, whereupon we have 3, 5, 7, and 9. Okay, so you have this one-to-one function, and now in terms of the inverse of this, okay, the notation, okay, so if we have the function in terms of f of x, now the inverse notation that we have regarding this function, okay, you're going to have, see, it looks like f to the -1, but this notation is just going to be the inverse of f of x. And relating to what we have in the order pairs, again, you're going to switch the order of the x and the y terms. So where we had 1, 3 before, the inverse is going to have 3, 1, and 2, 5. In the one-to-one, we have 5, 2 in the inverse, and 3, 7, okay, comes out to 7, 3. And we have 4, 9 in the one-to-one, and the inverse is going to have 9, 4. And for what we have in the case of the domain and the range. Okay, and where we had the domain in the one-to-one function to consist of 1, 2, 3, 4. Notice for the inverse, we had the x values at 3, 5, 7, 9, and for the range, it would come out to 1, 2, 3, and 4. Okay, so what we have in the domain, that is the x values we have in the one-to-one function, we're going to have in y in the inverse, and also for what we have in the case of the y values in the one-to-one function, we're going to have in x in the inverse. All right, and again, just to kind of restate, a one-to-one function and its inverse. We'll have interchanging x and y values. So for what we have, okay, for f of x with the coordinates as they are laid out, okay, that is going to be once again a case of a one-to-one function. And so if we take as another situation here, okay, say if I have, let's say g of x, and we'll say that we have g of x, we have among the order pairs, okay, we'll say we have -1, -4, 0, 6, and 2, 13. And just for what we have in the case of the domain, again, you have your set of x values, so you have -1, 0, and 2. As for what we have in the case of the range, again, we have the set of y terms, so you have -4, 6, and 13. And for what we have, so if our function is g of x, well, the inverse will be the inverse of g of x. And again, we have switching the order of the x and y values. Okay, so you have first order pair. Okay, we have -4, -1, and then we have, if you notice, okay, I have g of x has a y-intercept at 0, 6, but the inverse instead is going to have the x-intercept, which will be located at 6, 0. And we have 2, 13. If I have that in the one-to-one, the inverse will have the ordered pair 13, 2. And just kind of reaffirming the earlier statements. Okay, and this time we have for the domain. Okay, so you have -4, 6, as well as 13. And for what we have in the case of the range, again, the y values have it -1, 0, and 2. And once again, notice the interchanging case. So the domain for one would be the range in the other, and vice versa. All right, now going back to our characteristics. Okay, and we have concerning functions that are one-to-one and functions that are not. They have posed the question. Okay. is the function 1-to-1. And so just taking what we have for samples of graphs here. And still working with the XY coordinate system. And we have just putting up just kind of a quick sample here. Okay, so if I have, let's say that y, and we'll say is equal to f of x is equal to 3x plus 4. Okay. Again, just to be a function, it has to satisfy the vertical line test. Okay, so for all values of x, if I run, let's say from end to end, you're going to have at most intersection with 1 point. Okay, so you have the vertical line test satisfied. So we do have a function and for what we have in the case of the horizontal line test. Okay, so if you go up, okay, so for all y values you have at most 1 point of intersection with the horizontal line. Okay, and so in this particular case, right, y is equal to 3x plus 4. Okay, that is going to be a 1-to-1 function. Now, let's say just another type of function. I'm still working with the XY coordinate system. And say if we have kind of a V formation. And say that we have here that y is equal to g of x, okay, is equal to the absolute value of x. Okay, so for what we have here, okay, now that is at least going to be a function, since it does satisfy the vertical line test. Okay, so at the intersection by at most 1 point, okay, between the graph and the vertical line test, okay, for all x values involved. And then for what we have in the case of the horizontal line test, what's going to transpire, okay, is that, okay, we have, you got the point of origin, okay, where you have, you're just touching the base of the absolute value function. But as soon as you get above, notice, okay, we have at the same y value, okay, we'll have intersection at 2 points in this case. And so for what we have here, the graph fails the horizontal line test. And because it does, now while the absolute value function is a function. It is not a one-to-one function on the basis that it fails the horizontal line test. Now let's say that if we have another situation say that for this graph, I'm going to kind of hand draw this the best I can. Okay. And we'll say that we have that y is equal to, let's say, c of x. Is equal to 3 times x to the 4th. And so for what we have, once again, taking what we have with the vertical and the horizontal line tests, so the vertical line test, you have the intersection at most 1 point. And for what we have in the case of the horizontal line test, it's kind of like with the absolute value function. Once you kind of get above the point of origin, or the origin point, you can have this particular scenario, and it's going to turn out that, again, the horizontal line test is not satisfied. So in this case, this is not a one-to-one function. And for what we have in the case, we'll say that for this particular graph, so we got say we have y is equal to h of x is equal to negative 2x cubed and for the vertical line test, so if I run vertical line through this, you have the intersection at most 1 point, so it is a function. And in terms of the horizontal line test, it's going to turn out that for each x value there is only one y value in accordance with the vertical line test, and for each y value, there's going to be only one corresponding x value, and you have the intersection by at most 1 point between the graph and the horizontal line. So both tests are satisfied, so y is equal to negative 2x cubed. That is going to be a case of a function that is one-to-one. Now, some things about functions and inverses in terms of how they come together. So have a one-to-one function and its inverse. Will compose together as x. This is a little bit of a throwback again, like the composition of functions. kind of like the open circle. Say you have say we have the one-to-one function composed with this inverse, where we have f composed with the inverse of f of x, and it's going to be looking at f of the inverse of f of x, and this will come out to x. And also, if I change the sequencing where I have the inverse of f composed with f of x, so you're looking at the inverse of f of x, and that is also equal to x. Okay, so if you have, regardless of the sequencing, if we have the composition, okay, to come out to x, okay, then you're going to have one-to-one function, okay, and just sort of tie this in. Okay, so composing together is x. You're going to have the graphs of f of x and the inverse of f of x. They're going to reflect each other. Or have symmetry with respect to. And this will be, okay, with respect to the line y is equal to x. And okay, so you just have, so we're going back to symmetry. So we have like the axis of symmetry, and we've had like the halves of an odd function to have symmetry with respect to the point of origin, and also we've had the halves of an even function have symmetry with respect to the y-axis. But for the graphs of a function and its inverse, you're going to have symmetry with respect to the line y is equal to x. And now, and which kind of leads up to, okay, if you're looking at drawing out separately, okay, a one-to-one function and its inverse. Okay, first of all, we can say that in the case of kind of going past the sets of ordered pairs, and let's say we have a defined expression for f of x, and so we have just crossing over, say you have determining inverses of one-to-one functions. And let's say that just first case here. After looking at determining the inverse, now say we have a linear function. Say we have f of x is equal to 2x plus 6. All right. Okay, so again, the inverse is going to have whatever I have for x and y in the function, inverse is going to have it the other way around. Okay, so first of all, okay, we're starting out with f of x is equal to 2x plus 6. Okay, and again, that f of x equals 2x plus 6. Again, that's just a functional way of saying that y is equal to 2x plus 6. And to cross over to the determination of the inverse, what I'm going to do here is that with this expression, I'm going to swap out y for x and vice versa. Okay, so crossing over to the initial setup for the inverse. Okay, so this is our 1-to-1, and the inverse for now, we have that x is equal to 2y plus 6. And what I'm going to do here is that with the interchange rewrite, I'm going to express this equation in terms of that expression y. So I'm going to rewrite x equals 2y plus 6 in terms of y equals. And in the pathway, I can isolate the y term by subtracting 6 on both sides. So I have here, for now, we have x minus 6 is equal to 2y. And again, just expressing in terms of y equals. Okay, first of all, I can take half of both sides. Okay, so I have x minus 6 over 2 is equal to y. And I can just switch the order. So you say that y is going to be 1/2 of the binomial x minus 6. And then just, okay, so this y, once I put or express in terms of how it's going to look in terms of the functional notation. So for this y, we're going to have for the inverse. Okay, so the first y, okay, this had sprung forth from f of x, but now for that particular y, this is going to be referencing the inverse of f of x. And you can write the ratio in compact notation. We have 1/2 of x minus 6, and you can also write that. If you were to itemize, like putting in terms of the slope-intercept form, so you can say that we have the inverse function is going to be 1/2 of x, and we have minus 6/2, which is going to be -3. Okay, and so either expression, either layout for the inverse, okay, is correct. All right, and in looking at what we have, at least from a visual perspective, so again, I have, in essence case, I have y is equal to 2x plus 6. And just an expression, okay, for the inverse, again, I have x minus 6 over 2. And just for the graph portions here, okay, so the 1-to-1 function I have as a red line, okay, and it has a steeper slope than the graph of the inverse function, which I have at 1/2 of x minus 6. And if you notice, okay, you have for y is equal to 2x plus 6, I have among the ordered pairs. Okay, so I'm going to have like 0, 6, -2, 2, 4, -2, and you have -6, -6, as well as -8, -10. Okay, and then for the blue line, which I have in referencing the inverse function, okay, notice you have switching out the order of the x and y terms. So I have -10, -8, in contrast to -8, -10. Now where we have similarity is going to be the point of intersection, which we have at -6, -6. Okay, so have these two order pairs are interchanging, as well as those two. And while the 1-to-1 function has a y-intercept the inverse is going to have the x-intercept. So you have 0, 6 in comparison to 6, 0. And both of these graphs are going to reflect or mirror each other about the line which I have illustrated in green, which is in reference to y is equal to x. Okay. So again, a one-to-one function and its inverse will have the graphs to mirror each other about the line y is equal to x. Right. Now, for what we have in the case of another determination of inverse, okay, and we can say that for what we have, let's say we have g of x is equal to 1/3 of x minus 4. And if I'm looking for the inverse of this, okay, so again, just laying the groundwork again. Okay, so you got g of x is equal to 1/3 of x minus 4. And again, g of x, okay, this like y of x earlier, that is a functional notation for what we have. I'm saying that y is equal to 1/3 of x minus 4. So I'm still on the page of working with the presentation of the one-to-one function, and then crossing over to setting things up for the inverse. So I'm going to again interchange the x and the y terms. All right. So for the initial presentation of the inverse, okay, so this is going to be laid out as x is equal to 1/3 of y minus 4, and I'm going to express that part in its own capacity in terms of y equals. So I got x equal to 1/3 of y minus 4. I can get rid of the fraction if I multiply the whole equation by 3. Okay, so to do this, I'm going to have 3x and 1/3 of y times 3, because that's going to be y minus 12, and getting y by itself. Okay. So I'm just going to add 12 to both ends. And it's going to follow that we have that 3x plus 12 is equal to y, okay, and then just switching the order, like taking the commutative property of equality arrangement, like going from b is equal to a is equal to b. Okay, we'll have that y is equal to 3x plus 12, and so for the inverse, okay, so you start out with g of x, and the inverse, we have the inverse of g of x is equal to 3x plus 12. And looking at the dynamics here, and so we have for this particular spread, okay, so you have a version of y is equal to 1/3 of x minus 4, and again I have this in a red line, and among the order pairs -9, -7, -3, -5, 0, -4, as well as 3, -3. Okay, you're going to have interchanging the x and the y values, and this will land exactly on y is equal to 3x plus 12, the inverse. And again, both of these graphs will have symmetry with respect to the line y is equal to x. Okay, so again, one-to-one function and its inverse will have interchanging x and y values throughout. All right, and now for what we have in the case of determining inverses of functions. And just a couple of functions here. Let's say that for the first one, let's say that y is represented by h of x, where that is set equal to 2x minus 8. And we'll say that we have for the other item, okay, and we'll say that we have a function y is equal to m of x. And we'll say that that is equal to x minus 7 all over 3. So for the next few moments, let's see what we get for the inverses of both h of x and m of x. Okay, tell you what, if we go ahead and look into the first of these functions. Okay, so you have y represented by h of x, okay, and we have that set equal to 2x minus 8. And if I'm looking for the inverse, okay, so you got the function, again, you have h of x is equal to 2x minus 8, and just looking at just kind of putting the functional notation at bay and just concentrating on what we have solely in terms of x and y. Okay, so we have, okay, for the one-to-one function, again, we have y is equal to 2x minus 8, and then looking at crossing over to the determination of the inverse. So again, I can interchange the x and the y. And so we're going to have here, we're going to have the x is equal to 2y minus 8. And if I solve the interchanged equation formation in terms of y equals, okay, so I can start out by taking both sides and adding 8. So looking at adding 8 to both sides, so I have that x plus 8 is equal to 2y, and then looking at dividing by 2. Okay, so for what I'm going to have for y is going to be 1/2 of all of x plus 8 and just switching the order. And we say that, okay, for what we have in the case of the inverse, alright, so we began with h of x is equal to 2x minus 8, and for the inverse, so this being the form of where we have the inverse of h of x, and you can say is equal to x plus 8 all over 2 or where we have the inverse of h of x Okay, and if I were to split this up, this would be at 1/2 of x plus 4. And once again, looking at how the graphs of the one-to-one function and the inverse in this instance, okay, will compare. And once again, you have another case of straight lines, okay, with interchanging x and y values. And again, both of them will have symmetry with respect to the line y is equal to x. Okay, so about 10, 12, 12, 10. You have the intersection point 8, 8. And then for the rest of you have like 4, 6, 6, 4, 0, 4, and 4, 0. So you got your y-intercept in one and x-intercept on the other. And you have like -4, 2, as well as 2, -4 among the other ordered pair combinations. And again, so x and y terms are in switched order between the graphs of the one-to-one function and the inverse. All right, now for what we have in the case of our function m of x, okay, and this is given as a rational function where we have x minus 7 all over 3. Again, that could have been written in terms of the slope-intercept form. We could have like 1/3 of x minus 7/3. All right, so looking at, again, setting things up to writing out, okay, just what the inverse of m of x will be. Again, so again, just getting back to focusing solely what we have in the xy coordinate system. So this m of x, okay, that's another way of saying y, and we have is equal to x minus 7 all over 3. And if I look at interchanging the x and the y terms, and it's often easy to overlook that particular thing, and if you find out that like your resulting y comes back to what you started out with, chances are you overlooked interchanging x and y. Now there is a case of where you can have the one-to-one function and its inverse to be one and the same, but that would be almost like in a case if you have like reduction in terms like y is equal to x, but it's like those relatively somewhat rare instances. And for what we have in the case of interchanging, so we have in the first phase for the inverse, we now have x is equal to y minus 7 all over 3, and I can take care of the fraction, so I can just multiply the equation by 3. So we're going to have here, we're going to have that 3x is equal to y minus 7. If I solve for y, okay, so I'm going to add 7 to both ends. Okay, so we have that 3x plus 7 is equal to y. Or in fact, okay, so we had that y is equal to 3x plus 7. And for what we're going to have in the case of the inverse, okay, so I started out with m of x, and then just for the inverse, so we have the inverse of m of x is equal to 3x plus 7. and just looking at how the graphs are going to relate. Okay, so you got m of x is equal to x minus 7 all over 3. And again, for the inverse, you have y is equal to 3x plus 7. Both graphs will have symmetry with respect to the line y is equal to x. And again, you're going to have interchanged coordinates throughout. Okay, you have like the y-intercept for 1 with 0, 7, which will be like in the other, you have the x-intercept at 7, 0. Again, you have the interchanging of the x and the y values between the lines. All right, and so for right now, we've had our one-to-one functions and their inverses to be linear, and not all one-to-one functions will necessarily be as such. And also I will mention, I'm going to bring up something about the domain and the range. And so far we've had, with all these examples, the domains and the ranges have been the set of all real numbers throughout. And I'm going to give you a bit of an exception, and this is going to get kind of analytical, perhaps more so than I would normally care, but it does serve a purpose, and it kind of goes back to fundamentals regarding the radicals, like working with real numbers, and also the principal square root rule. And let me give you just a bit of a segue to what we have for determine the inverse of a function that is one-to-one, but it's not going to have all real numbers for the domain or the range. Okay, and let's say that if I have, first of all, if we look for the domain and the range, let's say, and we got f of x is equal to the square root of x plus 4 followed by the subtraction of 3. Okay, now for what we have on the side of looking at the domain, okay, for the domain, you're looking at keeping your x expression where I can keep the overall function as a defined relation or term. Okay, now you have for the square root of x plus 4 followed by the subtraction of 3. Again, our x expression is the square root of x plus 4. And again, since we're looking at trying to work with the real number system, okay, we have an even root radical with the square root, and because we have a square root, x plus 4 cannot be negative. Now it can be 0 or positive. Okay, and looking at configuring what the domain is going to be. First of all, we have that x plus 4, okay, is going to be greater than or equal to 0. And getting x by itself, okay, if I take 4 away from both ends, okay, it's going to turn out that, okay, to keep f of x as a defined function, okay, the values of x have to be greater than or equal to negative 4. So this is going to lead up to where we have, for the domain, and if I express in interval notation. So we're going from and including -4. So this will be in the bracket, and we have going out to infinity. So that would be the domain of this given one-to-one function. All right, now where the range is concerned, okay, so you have f of x equal to the square root of x plus 4, followed by the subtraction of 3. Okay, now, and this can get rather analytic. Okay, now, for the square root of x plus 4, okay, now, if you recall, with the principal square root rule, okay, now the square root of an expression cannot reduce to a constant that is negative. Okay, so that means that the minimum value that the square root of an expression can reduce to is going to be 0. And again, this is with the principal square root rule. So again, the minimum value possible for the square root of x plus 4 is going to be 0. Okay, and again, now we got f of x equal to the square root of x plus 4 minus 3. Okay, and so just looking at the minimum possible value for y, we're just kind of transporting. Okay, so you got like your y or f of x. Okay, so you have the square root of x plus 4 minus 3. Now keeping in mind the minimum possible value for the square root of x plus 4 is going to be 0. So if I consider this, okay, so you have like y is equal to 0 minus 3 okay, so the minimum possible value for y is going to be -3. And so we're going to have, in the case of the range, you're looking at your y values. Okay, so the very minimum value that y can possibly be is -3, and everything else is going to be higher. So once you get like x at -4, -3, -2, and then out into the positive values of x, okay, you're going to have the y values to also increase, and this is going to be the range of this particular function. Okay, I'm going to put, so this is what we have for the domain as well as the range of this particular radical function. Now, and just to sort of tie this in, now this is a one-to-one function. And if I look for the inverse of, again, this radical function, okay, so you have the inverse of f of x is equal to the square root of x plus 4 minus 3. So just, okay, so just kind of like, again, so f of x, functional notation for what we say is y. again, just like what we have done earlier, crossing over, okay, just translating from f of x to just y, and then interchanging the x and the y to initiate the formation of the inverse function. Okay, so we're going to have in the rewrite, okay, so we're going to have that x is equal to the square root of y plus 4 followed by the subtraction of 3. And again, I'm going to be solving for y, and I can isolate the radical term by moving the 3 over and adding. Okay, so now I'm going to have x plus 3 is equal to the square root of y plus 4. Okay, and I can take care of the radical upon squaring both sides. Okay, again, for the square of x plus 3, you have x plus 3 times itself. So you're going to have x squared plus 6x plus 9. You'll have is equal to y plus 4. And again, if I take y and isolate, okay, so if I take 4 away from both sides, so we have x squared plus 6x plus 5 is equal to y. And again, just interchanging. So y is equal to x squared plus 6x plus 5. And we're going to have officially for the declaration of the inverse, at least on the side of the function notation. Okay, so inverse, we have the inverse of f of x is equal to x squared plus 6x plus 5. But there are going to be some constraints involved, and this goes back to the domain and the range portion. So let me go ahead and kind of do a bit of a... Okay. So we have this particular layout, and so this is the function we started out with. And it got the domain and the range, and just and just put these categories, these items together. Okay, so you got your function f of x is equal to the square root of x minus 4 followed by the addition of 3. Again, we had for that particular function, okay, the domain consisted of the values of x greater than or equal to -4, and the range you had the values of y greater than or equal to -3. So this is our one-to-one function. Now for the domain and the range of the inverse function. Okay, so if I had to go back and just identify or specify the domain and the range. To make the whole packaging in terms of a one-to-one function. Okay, and okay, so on the basis of starting out with our one-to-one function, okay, we have again the constriction. We had the domain to be the values of x greater than or equal to -4, and the range to consist of the values of y greater than or equal to -3. And remember, a one-to-one function and its inverse will consist of interchanging x and y values. Okay, so just kind of doing a little bit of crisscrossing here. Okay, so we have, so what was in y for the one-to-one function, we'll have for x in the inverse. And again, what I had in x for the one-to-one, namely this radical function, and we'll have in y, or in the range, for the inverse. Okay, so we have values of y greater than or equal to -4. So one-to-one function and its inverse will have interchanging domains and ranges. And we have for the final portion, and just looking at the graphical layout. Okay, and if you notice, okay, we have again, we have with our radical function square root of x plus 4 followed by the subtraction of 3. I have this dark graph here, and you have like the y-intercept at 0, -1, the x-intercept at 5, 0. But now for, let me mention this, for the quadratic function, to make this one-to-one, it's not going to be the entire graph of y is equal to x squared plus 6x plus 5. I had to constrict it to where you have only the values of x greater than or equal to -3. So I had to kind of like lock everything to the left of x equal to -3. So I had this hooked section to where throughout from start to finish between the one-to-one function and that graph, you will have interchanging x and y values throughout. Okay, so to represent as one-to-one, you got that quadratic function, but constrained to only those values x allowed to be that, which will be those greater than or equal to -3. So again, a one-to-one function and its inverse will consist of interchanging x and y values, thus interchanging domains and ranges.